Hi everyone, I'm going to show you how to do the numerical simulations of the tribology performance for this case, where this is test is based on the block on ring test based on STM G77, and there are two material for this, a pin and the ring, and the ring is rotating at 1400 rpm with this speed, and there is a normal load applied to the pin ranging from 0 to 60 newtons, and the test is performed at room temperature, and there is a temperature measurement placed near to the pin, exactly near to the pin ring sliding surfaces during the experiment. And here we have the information about the test sample, which is the material, pin and ring and bearing. We have the pin and the ring are of the same material, bearing steels with 58 HRCs, and the liquid lubricants is the lubricating agent. It can be liquid, oil, or it can be grease. So here you want to study the frictions. You want to study the heating effect between the pin and ring sliding surfaces. So here how it looks like for the test setup. So you see the pin, you see the ring, and we can record the temperature measurements using this thermocouple, and we can record the rotations, and also as well as RPM. And here how it looks like in the FE model. So we have the normal force applied to the pin, and the pin here we assume it is elastic plastic material, and for the ring is a rigid body in this case, where we want to see how much the pin is deformed in this case. And the rotation speed here for the numerical analysis, we will convert it to from RPM to rad per seconds, so we can get the we can convert this using the in the internet online. And here is the oil tank. So what we want to measure only this pin and the ring only. So but then during the numerical analysis, we will set it to 12 seconds. It can be 20 seconds, it can be 40 seconds, it's up to you. So here we set it 12 seconds, and we, instead of having a normal force from the top, so we will replace it with the rigid body. Ring rotates upwards, move upwards in the same direction. So here we say that we can set it 0 to 2 millimeter or maybe to 4 millimeter within 12 seconds. And the pin here is assumed to be elastic plastic material, and the ring here, although they are of the same materials, but then we assume it is a rigid body, which is non-deformable body. So with the rotation speeds 146.61 rad per second, where we already converted from the RPM. And in this case, we learned that from since the friction coefficient is the input to the simulation, so from the experiment we obtain is 0.08. So this represents the lubricating effect between the pin and ring sliding surfaces. And this is how it looks like. So for the material properties, since it is important input to the numerical simulations, so for the bearing steels we get the general material properties from the web. So here is the information, or maybe we can get from the papers, from any articles, scientific articles. So what we're going to do is we're going to do the thermomechanical simulations. So meaning that we need to have a mechanical properties, the general properties, density, Young modulus in unit gigapascal, and Poisson ratio. And we need to have a thermal conductivity here, 46.6, and specific heats, since both information from these material properties is very they are very important to as an input to the numerical simulation, since we are doing thermal mechanical simulations. And this is the case for the this is results obtained from the this one source from Muhammad Abdullah. So from a 3D finite element model of rolling contact fatigue from this Tribology letters. So we learned that he already had the information through stress and plastic strains. So we extract the information based on this plot, and what we obtain here is the effect, the true stress through strains 0, 0. We assume we take 1.0 1800, and then we assume 0.02 around 2400, and 2500 here 0.04, so around here 0.04, so up to 0.1 value. So this is the information needed for the simulation. So let's not waste our time, we move on. We open the finite element. Okay, we have it. So first we need to open the model. This is we open this, not open, we go to import, and then we go to IGES file. This is the model where I created using the SolidWorks. So we have the assembly block, we have the ring and block, and then we assemble it. So we want the assembly, so we go and find it using this format IGS. We open and make sure that you choose millimeter, and now we have the pin and ring. Okay, so first of all we need to name them first. So here the first the top part is the pin, enter, and the second part is the ring. Oops, ring. Okay, now we already have both, and what we need to do now next is the meshing. Since we already have the geometry, so you can move them, you can use, you click here to move them like this to change the perspective, or you can press on Control and then click on the left button of your mouse, and then you can rotate. So now we have this view. So we click on element and mesh, or we can go from here as well, element and mesh, and we can choose the solid measure, since this is a solid object. So, or maybe it's easy to use here, the right button here. So element mesh, and then we go to solid measure. So this is for the steel, for the solid. So we can change this to 0.5. It depends on your computer performance as well, and also to depends on your requirements. So I think 0.5 is okay, and then click try meshing automatically, and it will do it for you to the both solid object, pin and ring. Just wait. Okay, now if you accept, you do not agree, you click reject. If you accept, you click accept, then done. So now you need to since we have the part here, now we can name them the mesh again. We have the ring and we have the pin. Okay, now since we have both this, what we don't need the geometry now, we can click here, since it's very annoying. So, or maybe if you want to untick this button, you can go to here assembly and part, and then click here. You go to assembly and click here. You can remove untick this button geometry, since this is geometry from the SolidWorks, and this on top two here is the pin element, the meshes. So now it's okay. So meaning that is the same. You can click here or there. So now next is we again looking at this here. We assume that this pin here is do not move, okay, in all directions, will not rotate at all in all directions. So we click here, we go to create entity first, and then we set the boundary SPC here, okay, click SPC and then go to create, and then we want to fix this in all direction. In we have X, Y, Z. This is the displacement X, Y, Z, and this is the rotation in X, Y, and Z. So we can refer to this X, Y, and Z. So now we want this pin do not move in all directions, and also do not rotate in all directions. So what need to do is we select the pick this object. So we cannot pick, we click pick here, but we need to select by part, so that we can select the entire part, not just the node or elements. So then we click here, we get all the part. So we click on apply. So now we have this. So we untick this button, we go to show and click none, so that this will not be this is not selected. So we go to the node. It is better to rename this part this. So we go to modify and we click here, we name this as not set SPC not 1 only, we name it after the pin, so that we easy for us to select this back later when we assign this for another task. Okay, now done. So what left is we click none, and we next part we must set this part, since we have two objects. So here we click on create. First we set the pin part, and we choose by part, pick, and then this one apply, and the second one is the ring, and we click on the ring and we click on apply. So then we have both. So we can untick the button so that we remove it from the selections, and what left is we define the okay, done. We're done with this. So what next? So we want to assign this this pin is fixed and the ring is rotating in Z direction, right? So rotating in Z direction only, and it can also displace in Y direction. As you can see here, it is displacement of the ring in Y directions and also rotate in Z directions. So what you need to do now, you go to the first, you need to define define this displacement and the ring rotations. So we go to or click all instead of model. This is the one that has been selected. So we go to all and we try to find the define. This is how we define the curve. We go to define. First we click new, and this is ring underscore rotate, ring rotate. So first 0 insert, and second is, let's say we set it to be 20 seconds. It's okay, and maybe we can set 12 seconds or 14 seconds. It's up to you. 12 seconds maybe. Yep, it's okay. 20 seconds. 20 seconds, and then we here we ring rotates, and the RPM is not 1400 RPM. You want to specify this unit in right seconds. 146.61. 46.61. So then insert, and then done, accept, and then we have it, then plot. So now we have it. So within 20 seconds it goes like this. So actually it is supposed to be in from the start 1.6.61. Replace, accept, and done. So we have this. Okay, so since beginning the ring will rotate from 146.61 right over seconds until the end. So next is we create new, and this one is the ring displays. Rings, you can specify the velocity. There are two things you need to know here. You can either specify the velocity, you can specify the displacement. Both, it's up to you. So velocity is also possible, but in this case I want to try it with the displacement. Displacement, ring displacement. So now ring displacement is start with 0. We can delete this first. Start with 0 and then 0 as well. Insert, and then up to we set it around 20 seconds, right? So let's say we set it 2 mm. 2 mm within 20 seconds. Insert, and then accept, and then plot. So now we have it. Okay, so we click on collab. So done with the define, and we go to the next where we want to set the movement of the ring. It goes up. So we go to boundary, and since we assume the ring in here is rigid, we select prescribed motion rigid, or if it's not rigid body, you can set prescribed motion set. It's up to you. So click new. So maybe you click just one here, ID number 1, ring rotates. So we select the part number where we already name it earlier. So here the ring is rotating in Z direction. So meaning that number 7, right? Number 7 here, DOF. So then we want to choose the velocity, right? The speed of the rigid body and node, so 0. And here is the one, the curve we defined earlier, ring rotate, and then we click done. So the rest, this is the scale factor. Either you can cut it by half, or maybe you want to change the direction of the rotations, so you can put minus. It's up to you. This is the scale factor, and the rest is nothing vector and that. Okay, just accept. And then next is we want to see that the ring displays. Smart. So in this case we select the ring again, but this is number 2, right? Number 2, the part ID number 2, and the ring move up with the Y translation DOF 2. And here we choose the number 2 since we assign displacement. So this to the rigid body, and here we choose this one. Since this ring, so Y here, and also the ring move up, so it's going to be positive, so then we set it scale factor is positive. So we don't need, if you want to make the ring goes down, so you set here scale factor with the negative, or maybe you can define it in the curve. Okay, so now done, we have this one. So click on collapse to minimize all these buttons, and done with that, we go to we specify the material properties. So the properties of the ring, the properties of the pin. So here we have the material properties we obtain from the web, and also from this one source. Just to tell you, this is not kilogram, this is gram of this is kilogram meter cube, so we need to convert this into millimeter. So then first of all, we go to here math, we try to go and search for the rigid, number 20 rigid, and here new ID, and here you put it rigid. And now the material properties here is the density in unit kilogram. So if we change it to millimeter cube, what we need 7810 E6, right? E minus 6, sorry, E minus 6, and here is in unit 210 gigapascal. So meaning that we put it 210 E3, since we want the unit to be megapascal. Megapascal is equal to Newton over millimeter cube, millimeter squared, sorry. So it means that here we set it 210 E3, so here Poisson ratio 0.3, and this is this. So okay, this is the case since this is the rigid body, right? Rigid body assigned to the ring. So we want the ring to be constraint applied in global directions. So meaning that in this case, for the first we call it for the first constraint, we allow this ring to move up in y direction only. So meaning that it is constrained in the z and x displacement, right? So we choose number 6. So right, let's see again, displacement constraints in z x direction, x and z directions, so it can only go up and down only. So we choose number 6. So second constraint is that this is for the rotation, degree of freedom for the rotation. We allow the ring to rotate in z direction only and constrain in x and y direction. So in this case, number 4, we choose number 4. This is applicable to rigid body only. Okay, then we done with this, we click on accept. Done. So then next is the we assign the elastic plastic material to the pin, although it is bearing still, but it is elastic. So we can use this power law plasticity if we have the value for the K, the Holomon curve, the constant K and the constant N, and the sigma Y. Since we do not have this, we only have this value, right? So this is we gonna use the piecewise like approach, where we choose the piecewise linear plasticity. So here we have we click on new, we click here bearing steel, and then this is 7810 E minus 6. Here is 210 E3. Here is the 0.3 and the sigma y. The sigma y here we choose 1800, 1800, and now we want to set the plastic strain failure at maybe it can go beyond this up to 1. If you choose plastic strain with 1, we can choose 0.5, we can choose 0.4. It's up to us. So in this case we choose 0.5. It's not a big problem since it is still is very hard, so it fails early at a lower strain value. It's normal. This is the part where I need to put in all this value, where all this value extract from this point. So now we try one. We key in 1 by 10810. This is the string value 0, and then 01800 and 002 to 400, 2400, 2500, 04, 06, we have here 0.01, 2750, we have 01, 0025. This is the value 3000, 0.05, and we have 0.1 and 3050. Okay, accept. So now we plot. Okay, so you see here the plot here is exactly the one you see here. Okay, so meaning that if we choose here, let's say we set the material to fill at 0.5 strain, so meaning that, but then the problem is that we only specify up to 0.1 only, right? So meaning that 0.5 is going to be 5 times larger than this. So with this factor of 5, is actually it will goes and read the value by approximation from the last reading. So meaning that it depends on the curve here. So then we done with this accept done. Okay, what left is that we want to do the thermal mechanical simulation. So then we need also to specify the thermal properties of this pin and ring material. Since both pin and ring are the same material, they are bearing steel, so we just choose thermal isotropic, but then we only do for one bearing steel, and then thermal. Okay, now we click new, and this is gonna be the same for density E minus 6, and for the HC, the heat capacity, we read from here 475, and the TC here we read here 46.6. Accept and done. So we click collapse, and now we have the material rigid, piecewise, and the thermal. So next we go to the sections. We click all and we go to section. So we need to assign this section to the both part, and this is the solid knot. So we choose solid, and then we see solid. Since both pin and ring is the solid, we just accept. And this is the case where we can choose anything we like, but in this case we just choose the default one, constant stress solid element. So this is just sufficient for this case, solid. And now we go to the part. Is this here. Okay, since I already named pin and ring here, okay, so meaning that we have the name here, pin and ring. So now easy for us to identify. So first we choose pin, and then we go to the section, we select, click on the dot here, we select the solid, done. And here the material for the pin here, you want it to be bearing steel with elastic plastic material characteristics. So we click here, and this is the equation of states. We leave it as it is. And this is the hourglass. If we want to use it, we can do it. If not, we just put 0 is default value. And lastly, this is adaptive. You can also use this if you have a problem with a severe mesh distortions to the pin during deformation. You can employ, or you can use this adaptive option, where it is for the remeshing. So it is applicable to the solid 3D tetrahedron. So it depends on the types of the elements. And this is the one, the thermal material property, where we key in earlier. So now we choose, since both pin and ring is from the same material, we choose this one only. So now accept. So meaning that pin is already signed. So now you go to the ring, we click here, solid, material here is rigid for the ring, and the rest we leave it as it is. We go to this and this here, accept, and done. So now click on collapse all. We go to the next, where we need to assign the initial condition of this test of this finite element model. So here the initial temperature here, we set it to be 20 degree. So you see here the temperature. So you go to temperature, initial temperature set. So we just we don't need to select either pin or the ring. We just leave it as it is. But here we click 20. But then here, why we put it here like this is because where we this gonna assign to all parts available in our simulations. So click on accept. So done. Click collapse, and then we go. We need to assign the contact between both. And before that, just to tell you something which is very important, where I forgot to mention. We go to the top, and okay, for the simulation, it is best not to have a contact like this in the very beginning. So you need to have some very small gap between the pin and ring. Okay, so how to shift this pin to move up a little bit, so that there is we can have some gap between the pin and ring. We go here. It is quite important, where I forgot to mention. Okay, here you go to element tool, you go to transform, and then you select by part. So we shift this part, the whole object of the pin, to the Y direction. So we shift this about 0.1 only. So you click on plus or minus, it up to you. So here minus meaning it goes down, so we click plus, so meaning now we have the gap. So we want it to be like this, we click accept and done. So okay, now we have this, we solved this issue. Okay, now next is the we want to assign a contact. What kind of contact between pin and ring? So now we go back to the model and part, we go back to the keyword manager, we go up and we click all here, we go to the contact. So you choose automatic surface to surface, okay, like this. Since this is 3D, we can choose this. But if you perform the 2D simulation, two-dimensional simulation, you should choose this 2D. Okay, 2D surface to surface or whatever, it's up to you, but you need 2D. But since this is 3D and solid, so we can choose this one. Okay, now we click new, and this is the pin and ring contact. Okay, then we have the friction here 0.08 for the static, and for the dynamic we leave it as is, it's not important. And forgot to mention, okay, here we need to assign which one is master, which one is slave. When we want to, in this case, we assign the rigid body to be the slave. Okay, so meaning that here the type of the slave we should choose based on the ID. Okay, so here we don't sorry ID, per ID we choose number 3, so then we can choose the ring. Okay, then for this case we can choose part, no problem, pin. Okay, and then we can choose here we want it to be the slave side forces included as well, we choose 1. And here also for the master side forces also need to be included. And here is the damping factor. We assume it is default 0. You can also put it 10%, so meaning that the ring will rotate, and then there is a 10% vibration occurs between this contact. So if we set 10, we can also set 5%, 20%, 30%, is up to you. But in this case we set it 0. And okay, so then we accept. We done, we accept. Okay, so we have it. Okay, now the segment, but the problem is that when during our simulations, during the simulation, the ring is rotating and then sliding onto the pin. So there is the pin surface will wear off due to the contact, due to a higher frictions. So then we need to assign the contact between the pin and this pin here. We need to change it to we cannot use part anymore for this master. We need to use segment. So in this case, what we need now is that we need to click here, we go to segment, and then we click on create, and this is the pin segment. So we choose pick by part, the whole part. So you see here, if I zoom in, you see the whole thing is selected. So let's say is one element is deleted due to the excessive contact, so the neighboring area, the neighboring elements will also be included in this contact. So meaning that when one element is removed, so then the next one will be in contact with the ring. So if you do not select this segment, so what happens is that when when one element has been removed, and then the ring cannot make contact with the next one, so the contact condition, the friction is not calculated. So in this case, we click apply. So we have it. So we click here, pin, none, and done. So now we go back to the surface. So we go here, we go to 0 since we want to select the segment set ID, and now we choose the ring here. Since we already make it one, so accept, done. Okay, so now click on collapse, and we go we finish with the boundary conditions. Okay, all boundary condition about the materials, about the frictions, about the displacements, about the these pins to move around and rotate, the ring rotates, all that boundary condition has been keyed in into the simulation into this finite elements model. And what now we want to perform this simulation, we need to go to control. So we're going to do the explicit simulations, not implicit. You can do the implicit, but now we focus the explicit. First, we want to do the simulation up to we set the termination 5 seconds or maybe 10 seconds, and then we finish with it. We click accept and done. And what next is the solutions. We go to our solution, we click on the solution. Since this is going to be the couple structural and thermal analysis, mechanical and thermal analysis, we choose number 2, and the rest we keep default and accept, done. So what next is this, since this is gonna be thermal simulations as well, so we click on thermal solver. Okay, now everything here we have. We need to select this. This is gonna be transient. This also gonna be non-linear problem with material properties, and the solver number 3, and then accept, done. So the next is thermal time steps, where here you can choose 0, 0.5, or maybe leave it as it is default, or maybe you want to do it variable time step, you can choose 1 or whatever. So you can also here specify 0.01 and 0 here you can 0.1, here you can set 0.01, is also possible. Or you can choose this one, you can set this is to be 1e minus 5 for example, and this is to be default for example, also possible. But to me, in this case, I set it to be default, accept, and done. Next is the contact. So we want to assign, we click on contact. Here we also, since we in this simulation we want to calculate the frictional energy in the contact, we select this number 1, and you can also play around with the scaling factor for the sliding interface penalty. Default is 0.1, so I just choose default. So then okay, we're done with the control. Okay, next is the since we want to generate data from these simulations, we need a database. We go to database, and we go to first we go to binary D3 plot. This is the most important here. So here we can set is 0.02, is up to you. So 0.01, for example, this is time interval between input. So we set 0.02, click accept and done. And normally we can choose this extend binary, and what we need now to let the string to be we want to write the plastic train data to D3 plot. So we choose one here, click accept and done. Or if you don't do this extend binary, it's also possible, it's not a problem. And the last thing is that SQ2 options, where when you click this, okay, so now you want the data for the thermal, you click on the T print. Okay, you can set this 0.1, or what you can do is that you just click here 0.01, click enter, so this will apply automatically to the rest of the point. So you go to first EL out, and then not force, not out, and also the RC force. I think that's it. Okay, click accept and done. So now we are we are finished. So what we need now, we need to save this file, not to use the same name again. So we save this block on ring, okay, with this key file format, and save. Okay, so then you click here, or maybe you can also click on top here, show we open this first. Okay, in order for you to open new, you can also click on the here, or maybe you can show the you click this start LS-Dyna analysis. Okay, so here. So if you want to this is the start LS-Dyna analysis, or you can click on this button. So here you choose the file. So you go to here, you click this and click on run. So the simulation will run it for you, and just wait until it's done. So it takes a longer time than what you see, so I think there is no problem. It needs more time since the mesh element is quite smaller. So it needs more time to do this. Okay, so it's starting. It depends on your computer performance. Okay, so I don't want to waste your time here. We can get back to this to see what is happening. So something is happening. It start to calculate, you see. So start with the first steps, and there will be next, but it takes time to do this since the mesh is quite small in this case. Okay, so we go to the one that I had earlier. So we go this is the data we have. So you go to D3 plot, click on and drag D3 plot to this. Okay, now we have it. So you can see this is the simulations. Okay, so okay, see the simulation. So you want to see it fast, you want to skip, you just click 5 here, enter, and it will go very fast, or maybe 10, so then it will skip 10 times. So if you done it just one, okay, then okay, now just want to show you how it looks like in this case. So let's say here we want to see the Y stress. We just click on the Y stress. You can see the indicator here showing about the stress, about the von Mises. Von Mises, you can see. So if we just wait, it's because of the computer. Oh yeah, maybe I need to stop since this is gonna take very long. So we just want to see the results, how I shows the results. So we can remove this ring since we done it. So you see the stress here. Okay, so the von Mises. So you can, okay, what you need to do is that you can go to this front also, or we just use left, and then we go like this, and then we can change the background to plain, for example, and then we can actually crop this using this, and we take this and then we copy, and then we can insert this into the slide. So now we have this. And if let's say if we need another information, not this one, we want it to be trace car, for example, you can also do it. Or maybe you want to show the temperature, you go to miscellaneous, you go to temperature, so you can see the temperature here. So let's say the temperature here, you see the temperature is around 90 degree. So what you can do is you just select this, snap it, and copy and put it here. So then we have this. Now you see we have this both for, this is the case for temperature, this information about the temperature, this information about the effective stress on so you need to be careful. You need to choose the increment, the states on the same steps. So okay, now I would like to show you how to extract information from these results. And you can also, you go to here. So here you can design, for example, in this case you want it to be between 0 and 100 for 50 only. So click here, or maybe 100 only. So now what you see here is this. Oops, sorry, 100. Okay, now you see 0, 100. So the indicator change is not gonna be dynamic, it's a user. So that's why you need to choose which one is suitable for you. And the next is the history. You go to history. Okay, so now just imagine that you starting from the start, and then you change this left, for example. Okay, this one, for example. Okay, now let's see. we want to know about the element. We go to nodal, so we click history, we click to element. For example, we want to know about the y stress, for example, of this element. We click this element and then we click plot. So we have the information here. You click here, so you can name them whatever you like. So for example, here you want to be plots. You want the plot y stress. So you need to name the file t.xt. So save and then quit. So next is you need to know about the, for example, the stress. For example, same elements, you click plot and then click save, and then here plot, here is von Mises, for example. So click save and quit. And this is about the, okay, maybe temperature. So you click plot, save. This is temperature as function of time. Okay, so we click here, we temperature. Okay, done, quit. And then we also need displacement, since it's going to deform. Let me just show you. It's going to deform, right? So we need to know about the deformations of this in the y directions. So let's just go and find y displacement and plot, and we have it. Y displacement. Okay, done, quit. Okay, so now how to plot this? So you go back to you open this, open the Excel file, and then you go to here. Now you go to open. Go to our all file. So we are looking for the txt. First you need the displacement y displacement. Okay, for example, this we open, we can click this, so they divide. Okay, they divide this. Okay, we have this. So now we need to rename. This is the plot, this is the time, unit second, this is displacement, y in unit millimeter. Okay, next is we open the temperature, since we have the displacement as function of time. The temperature, we go to the plot, temperature, open. So if we choose this delimited, so we cannot have this like this, so we need to set to fixed, so that they are separated into two columns. So now we only need this. This information, the time information is still the same. We click press Ctrl together with the Shift and down button. We select all in this column. We set it, copy paste here, and then we name this temperature, degree, and Celsius. So now it's because this is scientific. So what we need now, we need to change it to general. So done. We have this information already. So here you see, right? So now what we need now, the data here, we have a lot of data. So so we can do the plot here, where this is the temperature as a function, displacement as a function of time. So but we don't need this. So what we need is this one. in this case. It depends, it's up to you, you can do whatever you like. So now we have this temperature versus displacement y, and this, maybe we can change this. Let's change. Okay, so we have here temperature versus time. So now done. Okay, thank you for watching us. Okay, so I think we stop here. So thank you so much for listening.